Thank you very much, everyone, for coming. We have another session of the seminar. This time, we have Maichel Aguayo. Actually, I met Maichel, yes, like 4 years ago. When
I think so.
A long time ago. But it was Diego the one that made it possible. So thank you very much to Diego for that. He's right now a professor at Universidad in Concepción. So he took a bus, I guess, today in the morning to be here. So thank you very much for the trip. And he'll be talking about his work on single commodity flow-based formulations and accelerated vendors algorithms for the high-multiplicity asymmetric traveling salesman problem. Right? Work is done with people at Virginia Tech as well. So thank you very much again, Maichel, for being here.
Thank you, Rodrigo, for the introduction. So this is joint work with Dr. Sarin and Dr. Chirag from Virginia Tech. So what is about the high multiplicity traveling salesman problem? This is just an extension of the well-known ATSP. Well, the definition of the problem, like you have a base and you have to start in the base and then come back to the base after visiting each customer every time once. So, and the design matrix is asymmetric. So that's the main difference, like for the symmetric TSP. And this problem has a lot of application in the industry, logistics, scheduling, among others. And here is like an example of the asymmetric TSP, like we took the street on Concepción. So imagine that here we have like the points that we want to visit in Concepción. This is like a car police that want to visit like some sector on the city that has a high risk like of like poverty or something like that. So here we took why we have asymmetric distance, because like we took the distance using like the Google Maps, and to travel in one direction is different to travel to another direction. So that's we have like the asymmetric. So here we start visiting all the nodes that we want to visit along all the axes, like are the streets, and then we come back. So that's a well-known problem that people have studied a lot in the literature. Like the most well-known like solver is like the TSP solver to solve the symmetric one. But also you can use that to solve the asymmetric using like a transformation that you create a new network with the twice or 3 times the number of nodes that you have in the original problem. But now we are going to talk about the high multiplicity. Why we talk about the high multiplicity? Here is the difference. Like now, a city can be visited multiple times. And this is a fixed number that is given. We have an asymmetric matrix, and this has been shown to be an NP-hard problem. So you take the number of visits to be 1, then you just get the regular ATSP. So here is an example, just to illustrate the problem. Here we have the base. We have like one salesman that is represented by 1 here. And then we have the different cities. Here, this is the only city that has to be visited twice. So, and the other cities, just you have to visit once. Here, the salesman start visiting 2, go to 3, 4, come back to 3, 5, and then return to the depot. Yes?
Do you visit other cities exactly once, or
no?
Visit at least once?
Here's the number. So this is the number that tells you how many visits you need. So this is like given. This is a parameter of the problem.
You cannot visit more than that.
No.
So there might be infeasible tours. Infeasible.
It won't be very infeasible because here also you can do self loops. Those also are allowed. So it's like you can come back to the same city again. So there are, I will talk about some application where this problem arises. So you will never have an infeasible solution, right? That's a good question. And so this is the problem that we want to solve. And so far in the literature, there has been exponential length formulation for this problem. And also it has been a polynomial one, but using a large number of variables that make it very, very difficult to solve directly, like in Simplex or Gurobi. So here are some applications where it arises. Like we have a study here, like in biomass logistics. So imagine that you have like a field that you have a lot of bales, like round or rectangular bale with corners over switchgrass, and you have equipment that visit these fields. So it might be the case that you have like a lot of biomass here, and you will need to visit that place several times. So here's one application. Another application, like in 2014, like the primary pharmaceutical manufacturing scheduling problem, where this problem, the high multiplicity arise, has a subproblem. So the chess problem, like also we have the landing airplanes. So here is small and old one example. Here is the problem. You have gates and you have the planes. So imagine that you have all the planes in the air waiting for landing, but now you have several planes of the same type. So there it arises the high multiplicity. Like you have a Boeing 747, but you have 4 of those. So on. So there is the high multiplicity, and the question is like how you land the planes in the gates so that you minimize like the total setup cost. That is the cost to assign one plane to the gate and then the other model to the same gate. So there is like this setup cost. And the notation that we are going to use in this talk is like we have a graph, directed graph. We have like the classical, the nodes and the arcs. And here we assume that 1 is the base city, where the Salesman starts and then compacts. Ni is the number of visits required to each city. And we have Cij, that is the traveling cost. That is asymmetric, right? So here, like I mentioned before, if you make it Ni equal 1, then you will have the regular ATSP. But in the ATSP also, you cannot have self-loop, visit the same city twice. And the definition, the objective, what we want to find out is a tour that starts and ends at the base city after having visited each city Ni times, while minimizing the total distance traveled. So that's the goal. That's what we want to find out. And here is like the formulations available in the literature for this problem. First, we have the parameters. N is the number of cities. We have Ni's, that's how many visits we require to that city. We also have Cij, that is the traveling cost. And we have the decision variable, that Xij. But here, there is a huge difference for the ATSP, that now it's not binary. It's an integer variable that denotes how many times we travel from I to j directly in a solution. All right, and also here you have the I can be equal to j. So here is the formulation, the basic formulation that we have. We want to minimize the total cost, the length of the tour, and 2 and 3 just said that each city is visited Ni times. You have to like visit and you have to exit it Ni times. And then we have the Xij's to be integer, and we have the subtrue elimination constraint. So the question here, how do the subtrue elimination constraint look like? How can you add those cuts? And here is an example. So here is a solution. So if you just solve 1, 2, 3, and 5, you can get something like that. You see, you start here, go here, you do self-loop, then come back. And here you have another loop. So what people shown that here you have, the graph has to be connected. So you have to have a path between one or a very pair of cities. There has to be a path. It doesn't have to be directed, but here we have like this that is disconnected to that set. So the cut that you use then is you have to have an arc from here to here. This is like a connectivity cut in the TSP literature that is this case. So this cut also will work in this one, and people like in 2006, Griever and Klander, they show that this is the subtrue elimination constraint for this problem. So you are requiring to have like an arc from this set to this set. Later, in 2011, Serene and all, they showed that that cut 6 is identical to 7. So that's the connectivity cut in the TSP, and this is the packing form in the TSP. So here, you are requiring, so you take out, you sum up the nice, you will have here, like you have a cycle because you have ni arcs. And to be valid, to be a feasible solution, you should have ni minus 1. So it's the same. You are forcing this to cut this subtour and will impose a cut to the other set. So you can show, like using 2 and 3, that these are equivalent. So this is nothing new, similar to the TSP, but here are like, this is like a new cut. And also, if you take ni is equal to 1, this also is a valid cut for the TSP. So you see, this is the same packing cut that you will have for the TSP. So here is, this reinforces that this is just an extension that if you make ni equal 1, then you will have the packing cut for the traveling salesman problem. So in 2011, the Seminario, they proposed a polynomial length formulation for this problem. They use PIJU. It's like a multi-commodity flow-based formulation to solve this problem. So this was the first polynomial length formulation available in the literature for this problem. And what they do, so they impose, here is like regularly like the multi-commodity, you have multi-commodity here and you want to send one commodity from the base to each city. So you have that, then you have a connected graph so that you will have like a solution that doesn't have any subtour. So here, these are the regular from the previous formulation, and here are the subtour elimination constraints that they proposed. They are saying, well, we send one, this is just one commodity to each city. Here is, you send one from the depot. Here you are forcing for each city different than the depot to get one. And these are just the standard flow conservation constraints. If you enter, you have to exit. And if you use the arc, it can be flow. And actually, you don't need this to be integer. By the total unimodularity property, you will have this take integer values automatically. So you don't have to do anything else. And this is the formulation that they proposed in 2011. Well, yep.
Where are the I values in that formulation?
Oh, here in 2, 3, and 6. So that's, I didn't want to cover it again. Yeah, so that's why I just put the number there. Just, all right. So this is just from the previous formulation, and this is the subtour elimination constraint that they proposed. That is like a multi-commodity type. So here is what we proposed. So we realized that we can make it more efficiently if we use an aggregated version of this formulation. So instead of using 3 index, we use a 2 index variable that represents the flow on the arcs in the solution. So we have the same, but here, this is what we have. We are sending, so here is the idea. What is the idea? If you have one, you were in this formulation that they have, they were sending 1 unit of commodity U to each city. We realized that you can sum them up, sending NIs, and then making sure that each city gets what they demand, the NI values. And we have that, so you can say, if you take NI equal 1, then this is the GG formulation for the ATSP problem. That also is very well known. So odds formulation reduced to the ATSP. So you can see it like an extension of the GG formulation if you want. And so here is like we send the total, like the total visit that we have to send to each city. If you use the arc, then you can send flow. And here, what enter to a node and what get out has to be the number of visits that you require. And then this is just, again, by the total unimodularity property, you don't need to make it integer. It will be automatically take integer values. And so the question is, okay, then we prove that this, how we compare our formulation, what is available. So the LP relaxation of the GK is like the exponential one with the cuts. Then the Sarin et al., we call it SSI, and our formulation, we call it single commodity flow, SSF, right? So we denote those are the optimal values of the LP relaxation. So we proved theoretically, so Sarin et al., 2011, they have proved that the LP relaxation of the exponential one with the cuts is identical to the multi-commodity flow. What we prove in our work is like, as you can expect, this is an aggregated version, so the relaxation will be weak. And so it's not as tight as the SSI, but it's a lot more efficient, all right? And also we found an example like where this is strict. So that means that there is an example where this is less than SSI. So how we prove it, this is just an idea how we did it. First, we generate a scale version of the previous formulation. What we did, we realized if in the previous formulation that Sarin et al. Were proposing, they send one. We said, you send a new, it will do the same job. You just are scaling the constraints. And we also proved that this doesn't require any proof. It's just, you are just scaling the formulation, so you will get the same solution. So we did a computational experiment, and like the difference is sending one or sending a U was like almost identical. So it wasn't any difference. So that's why we use the other formulation. But we define this one that we send a new instead of one. And then we have to, also this one, we have to scale this constraint. Because previously it was one, but now we could send a new. So that's what we have to scale that formulation. And then the second part of the proof is like, okay, if you make this variable equal to that sum, if you add the map over the U, you have this over the U, this over the U, this over the U, you will get the formulation that we proposed. So, and then we just show an example where the inequality holds, and then like we are done. So that's how we prove it. And so that's with the formulation. So far we have like a new formulation for this problem that's like is polynomial, right, and has like less variable. But theoretically, it has a weaker LP relaxation. So there is another very easy way to solve this problem. If you copy the city n times, then you can get ATSP solution. So then you can use the state-of-the-art algorithms to solve ATSP. You could use Concord, you could use the most effective formulation for this problem, branch and cut, branch and bound. But what is the problem here? When you make this transformation, you are increasing the number of nodes in Ni plus 1. If the Ni's are very large, then you could have like a original network with 10 nodes, but the resulting network can have easily 1,000 nodes. So it depends on the inputs of the problem. So that's like the main issue there.
When you're copying or multiplying a city, what do you do with the limit in these cities? You put a high cost? Or?
No, we put the like, so we have to change the matrix accordingly. So you copy, let's imagine you have city 2 and you copy it twice. Then you have to copy the distance 2 to 3, 2 to 4, and the copy of 2 will have the same distance. It's the same of the copy of the cities, it depends on the parameters. So in some problems, the value can be 0, can be infinity, so it depends on the problem. Like in practice, it will represent, so imagine that you have a Boeing 747, you want to allocate to the same gates another Boeing 747. The question is, how much is how is the length of the setup cost? So that will be the self loop that you are requiring the same kind of products. Like also, this is like in production when you have lots. So imagine you have a chair, but you want to produce 100 chairs. There's no chair 1, 2, and 3 because it's the same chair. So you don't have to. That's why you use like an encoding that is called high multiplicity, and the high multiplicity has been studied a lot, like in the scheduling literature. You have flow chop, job chop, single machine with high multiplicity that it has more applications. So that's the main problem, that you are increasing the size of the network, but you could use any approach. So we also tried this one to see how it behaves. And so now you have like the new n is n hat, right? And so you have the ATSP formulations that if you replace ni by 1, then you have these subtrue elimination constraints and so on. So we took the most effective formulations to compare with, that are the GG, MTC, and DL, based on the work on Roberti and Todd 2012. So they make like a comparison like with the formulation, and this is what they report. These are the most effective ones. And in my experience, like the GG like can solve 100 node, 400 node to 1 hour of CPU time. So that's another approach. So far we have the direct formulation. Then we have another easy approach, copy the city, solve it using TSP tools, ATSP tools. Well, we have a 2-index formulations, so we wanted to apply vendors decomposition. Why? Because if you look at the structure of the proposed formulation, the X are integer and the other ones are just real variables. So you can easily decompose it and make it so like a master and a sub problem. So here we have the master problem where you have just the X variables, and the sub problem take all the Y variables, and then you took the dual and you can implement like your own vendors approach, or you could use the vendors approach available in Simplex. That's the latest version has it. So we also prove our result. We try our result and compare with what if you use the automatic vendors in Simplex. So we also have those results. And so here you have like the master problem, then you have the vendors cut that you are adding from the sub problem. Well, we proved that if you do that, the vendors cut is identical to this connectivity cut that you will get. It is identical that, so to sum up, if you apply vendors to the single commodity flow, it's the same that using the exponential GK formulation using a relaxation approach. But you only generate subtours from integer points. That's what the conclusion is there. If you are generating cut from, you also could generate cut from LP points and add them to the master problem. So what we did, we said we implement first the regular vendors, and then we realized that instead of solving the dual, you can exploit the structure of the primal. What does it mean? So given that you have, what the vendors do is like you have the solution, and now you look for cuts. So, and to do that, it will use an LP solver. And when you have large instances, it will take a lot of time. So it's not very efficient for so large instances. So what we did, we exploit the primal, and we said, okay, we can easily, once you have the X values, we can identify the subtours. Like if you see the set 1 will be all these, and we add the cut that the set 1 has to be connected to the set 2. So you don't have to solve an LP relaxation to get the cut. You can do it more efficiently, like in milliseconds, if you write your own code. Well, we also, to speed up the vendors, what we did, okay, but you could have a lot of tours. You can have a lot of sets. Why don't we add all the cuts at the same time and see what happens? And what we found out, that this is a lot more efficient. Adding all the cuts can reduce the time like by a lot. It's very significantly. And you could expect like you are like taking too much memory or increasing the size of the tree and so on, but it won't be the case. And so we explore the primal, then we generate all the cuts, and finally we implemented using lazy cuts. That's available in Simplex and also in Groovy and other solvers. So what we did here is like, so you relax the subtrue elimination constraints, you start branching, and then let's see we are here. The solver will tell you, I have an incumbent solution. And when the solver, it's like the solver take care of the integer values. We don't do anything with the fractional solutions. Once we have the integer values, we generate the cuts. We have the cuts. So every time Cplex tell us I have an incoming solution, we check if it's feasible. If doesn't have any, if it has any structure, then we have all the cuts, and then we start solving again. And we do it in a branch and cut framework. So this is like parallel. So like usually the vendor is like sequential. You add the cut, solve, add the cut, solve. But we tried, and it wasn't very effective for this problem, and this was a lot more effective. So we also solve extension of this problem. The first one, what happens if you have multiple salesmen? Let's say you have two, and these are the visits, so one salesman go here, and the other salesman go here. So it could be the case like in biomass logistics, you could have multiple equipment loading out like SSLs or storage placed. And also another extension, you could have multiple depots and multiple salesmen in each depot, and then they have to come back to the original depot and so on. So we try also, we study this problem, and we propose formulations and also vendors, accelerated vendors for them. So now, oh, I have time? What time is, yep. I'm fine? All right. So the computational results, first we use problem instances from the literature. We use TSP library problems, Cisareva and all, and Robertian taught, and we try instances to 1,000 nodes, all right? We didn't try any larger, and we stopped just in 1 hour. So we use Cplex 12.7.1, and we use LazyCat, and also we use the automatic vendors available in Cplex. And all runs were made like this is the computer and 1 gigabyte of RAM, and running in Ubuntu. Right? So first, these are the results for the formulations. Here are the problems. These are from the literature. These are the number of nodes. We go from 43 to 443. Here's how we generate the number of visits. They were generated randomly at first, but then we did like a sensitivity analysis and so on. And here we compute, this is the single commodity flow, the formulation that we propose. This is the LP gap, the integer solution at the time. And here is the formulation available in the literature. So you see, our formulation can solve to 43 nodes in 1 hour CPU time. But this one fails like in the hundreds. And if you compare the time, like this is almost 10 times faster than what is available out there. 6 seconds, 700 seconds. So there is like a huge difference.
What's the column T/tab?
Oh, here we didn't want to add another column. So here, if we report the time, then we got the optimal solution. If we didn't report the optimal solution, then we report the gap. Okay. All right? So sorry for that. So here, like 0.18 was, it was in 1 hour, that's the gap. But this one, you see this one solve all of them to optimality in the time, but here, this one, the gap, almost 0.2%.
What's the time limit in those?
1 hour, 1 hour CPU time for all. So here is like a huge difference. And here, so then we took to 600 nodes. What happened? Here are other instances from the literature. And this one couldn't solve any of those instances over 100 nodes. But this one have some gaps here with hundreds, 200s. Here we solved 300, but after the 500, it got very difficult. So with the direct formulation, we couldn't solve any and couldn't find any feasible solution. So what are the conclusions from here? That the single commodity doesn't provide like very tight LP relaxation, but it's a lot more effective when you solve it like using Cplex 12.7. The available formulation can only solve 200, but our proposed can go to 400, almost 500 nodes. So that's why this could be important, because like there are some problems where the high multiplicity arises like a sub-problem. So you could use our formulation to solve that problem and speed up the overall solution approach. So now, we present result. What happened if you transform the solution to an ATSP representation? Here is the problem. Here is the original number nodes. Here is the NI values, how we generate uniform, like between 6 and 10. Here are the number of nodes in the resulting network. Like here, in the original problem, you had 171 nodes, but here you got over 1,000 nodes when you use the transformation. So here, to solve like this problem, you will have a network of this size, over 1,000 nodes. And then we solve using the SSI, the existing one, or formulation, and if you use DL, GG, and MTC, that are the formulation for the TSP. So all formulation outperform all of the other ones, and if you start using ATSP, it couldn't find any solution in 1 hour of CPU time. So it fails around like the 200 nodes. So it couldn't, evenly like the original problem was just 100 nodes. When you go to 200, it couldn't find any. So the structure wasn't very nice for the formulation. And then, so from that, we can see that it's not very efficiently to use ATSP formulation. So someone can ask, why don't you use Concur and so that? And we did that, but in another paper that we use this same idea for the ATSP and MTSP that we just got published. There we show that our results are very competitive with Concur. We use just the regular Concur without any change, like a normal person will do, and we just compare with regular simplex. So we were very competitive with that. And here is like, what happened with the vendors approach? Here we have the instances. We implement all the standard vendors. Like you will do solving the dual of the subproblem, generating the cut using an LP solver like simplex. Here we use that approach, but now we use a strong non-dominated cuts that you are a stronger cut that the regular vendors want. And here is the automatic vendors. You just have a command there, and vendors do automatically for you the decomposition. So the vendors, like to the 100 nodes, outperform the others one, the one that we implement and the one with no dominated cut. But over the 600, it start failing, like the gap is huge, 90% gap in 1 hour of CPU time. So then we just took this to compare with our approach. And here we get to 1,000 nodes. So the same number node problem. So these are the standard problems. And here's the optimal IP solution. Here is the simplex time. So you see simplex over the 500, the gap is 90%. And here couldn't find any feasible solution. But our approach can solve all of them with a maximum gap of 1.45%. So it performs very, very well. And in the others, like the 1,000, we found the solution like in 33 seconds, and so on. So here the problem is like, when you solve the subproblem with an LP solver, when you have large instances, it's very difficult. It takes a long time. But if you can exploit the structure of the primal, you can get cut like in milliseconds. So that's a speed up the overall solution approach. Then we use the same idea for the other problems. And here I won't present any table. I just will sum up what we found, that the accelerated vendors like outperforms the single commodity formulation when you solve it directly, and the automatic vendors available in simplex. So we also were able to solve instances to 1,000 nodes in 1 hour CPU time to optimality. And these are new problems. We introduced these too. And there does not exist like any algorithm to compare with. But we could solve to 1,000, and like we compare our solution just with the automatic simplex. So just now the concluding remarks. We have first proposed like an effective formulation for the HN ATSP. It's not very tight, has the best one available, but it's very effective. We also introduced, right, an accelerated vendors that can solve instances 2,000 nodes in 1 hour CPU time. And these are the large size instances solved to optimality in the literature. And we also introduced 2 variants, like new problems to literature, like single based, multiple based. And likewise, we use like the same approach. And we were able to solve 2001 cities, like in 1 hour CPU time. Here's like the notes on the contributor. So it's Dr. Seren, right? So he's my advisor in Virginia Tech, and he worked in scheduling and routing problems. And also Dr. Chirali, also like he also is a retired professor at Virginia Tech, but he's retired, but he's still writing like 15 or 20 papers per year. So, and he's retired, so he's very active. And we are working with him in several other papers that we have. And here is like, so you want more information, here's the reference, here's the paper that it was accepted like in July after several review and so on. And here's like the details, so you want to find more information. Thank you for coming, and thank you for your attention. So.